These are the notes on galaxies. So in the raisin bread dough analogy, obviously the raisins represent your typical galaxy, okay, or you could say clusters of galaxies would make it even better. And then the dough itself would just be the emptiness of intergalactic space, empty space. So each raisin moves away from every other raisin in the dough. The farther apart they are, the faster they move apart. That's basically Edwin Hubble's law. The farther, the faster. The farther apart you are, the faster you move away. Now keep in mind that this would appear this way no matter which raisin you were on. It would look like all the raisins are moving away from you. The only flaw in this analogy is that the bread has a surface. So that doesn't really correspond to something in the universe. So if that bread dough just kept going and going, it would be a very good analogy. So remember, we were talking about the web structure of the universe, right? Which is basically saying that space is clumpy, and it has been since the early universe. So matter was concentrated in clumps or strands of the web. Well, over time, those strands, those clumps, pulled themselves together because of gravity into galaxies. Galaxies are in every direction. This is a very, very tiny picture of a very, very small part of the sky taken by the Hubble Space Telescope, named after Edwin Hubble. And every one of these things that I am turning yellow is a galaxy. A few of the objects in this image are stars in our own galaxy, but everything else here is a galaxy. So there's galaxies in every direction. If you were to zoom in outer space, in any direction that was not obscured by a space cloud, by a nebula, you would find galaxies in every direction. There are many kinds of galaxies. We are going to talk today about the classification of those galaxies, just so you get the impression of just how many galaxies are out there. I think if you just learn how to classify them, which is actually a pretty easy skill, it's not very hard, it'll give you the sense, and you'll probably remember that, oh yeah, there's a lot of galaxies out there. So this image shows elliptical galaxies and what we call irregular galaxies. Let me just say irregular galaxies are galaxies that don't fit into the classification system I'm about to show you. So if you do find any that don't fit into the classification system, well, those will be called irregular. The abbreviation for irregular is IRR. IRR is the abbreviation for irregular galaxies. But most galaxies do fit into the classification system that Edwin Hubble himself came up with. To talk about galaxies, we need a working definition. So I'm going to say a galaxy is a cluster of billions of stars. Now, that is not the entire definition of galaxies, because galaxies have a lot more than that. But they always have that, so I'm going to use that as the definition. It turns out most of the galaxy is not just the stars. There's also the surrounding nebula, which is, you could think of it as gas. And then there's also the dark matter. Well, that's the big hanging question in science, finding out what dark matter is. But at this point, we can't speak to it too much other than that it has mass. That's all we can say about it, really, truly at this point. So galaxies have a lot of dark matter, and then most of the rest of them is actually nebula, but they always have billions of stars. So that's the definition I'm going to use. Galaxies have different parts. They always have a nucleus, which is the center of the galaxy. Sometimes that's all they have. They also often have spiral arms. They're called spiral arms because they wrap around the nucleus in a spiraling fashion. Now remember, not all galaxies have spiral arms. It is thought that most galaxies start off with a nucleus and spiral arms. Then depending on what happens to them, which other galaxies they combine with, and other explosions that can occur in the nucleus, that alters their form, that alters their classification. If we go out to a very, very dark place, like up on a high mountain or out in the dry desert where the sky gets very, very dark, if you're far away from a city, well, the Milky Way looks something like this. This is part of the Milky Way. This is the Sagittarius portion of the Milky Way Galaxy. That doesn't appear to have much structure. Looking at that, I would say irregular. But remember, we are in the galaxy. Because we are inside it, it's hard for us to stand back and look at its structure. So we do know the structure of our galaxy by plotting the positions of all the stars we can measure. We have a very good idea about the structure of our galaxy. We just can't see it by looking at the sky. The word galaxy comes from the Greek word galaxias, which means milky. Because the ancient Greeks looked at the sky and it said it looked like a milky river through the sky, a Milky Way, and that's actually where our galaxy gets its name. So the word galaxy kind of means milky. So it's kind of a little redundant to say Milky Way Galaxy, but we say it anyway. Our particular galaxy that we live in is called the Milky Way Galaxy, and our galaxy is a cluster of 100 billion stars. Not just 1 billion stars or 10 billion stars, but 100 billion. Some estimates say that it might be as many as 200 billion, but we do have a ballpark estimate in the 100 billion range. Our galaxy is called a barred spiral galaxy. That was Hubble's classification of galaxies. How do we know it looks like this? Because we can plot all the stars in our galaxy and then put them in a computer model, stand back, what would it look like from above, and this is what we get. So our nucleus, notice, is not round. It is actually shaped like a bar, like a candy bar. Luckily, there is a candy bar named the Milky Way that might help you to remember this. We've known this for about 30 years, that our Milky Way galaxy does not have a round nucleus. It has what we call a barred nucleus, putting it as a specific type of galaxy under Hubble's classification, a barred spiral. Now, we are not in that bar. We are located in the spiral arms. About 2/3 of the way out from the center in those spiral arms is where our solar system is located. There are some galaxies that don't have spiral arms at all. These are called elliptical galaxies. So elliptical galaxies range from round to oval in shape, and eventually they get very, very flattened as you go from 0 to 7. They're E0, E1, E2, E3, E4, E5, E6, E7. By the time you get to E7, the ellipse is so flattened that it almost looks like a little line. Some people describe that as a lens, okay, like a contact lens. Very, very, very flattened. So these do not have spiral arms. So why not? Well, a lot of computer models seem to suggest that elliptical galaxies form when two spiral galaxies collide with each other. Depending on the geometry of the collision, that gives rise to a different shaped elliptical. So if they collide with each other sort of perpendicular, like they're coming in from like at 90 degrees, then they would form maybe an E0. If they collide with each other, they're coming in almost directly a head-on collision with each other, directly opposite, they might make an E7, and everything in between. So it takes a while to go from the collision of two galaxies to a new merged galaxy. It might take hundreds of millions of years for this to happen. But there is one hypothesis that elliptical galaxies are formed out of the collisions of two or more spiral galaxies, although there are other potential ways for them to form. Edwin Hubble's classification is shown here. Notice the elliptical galaxies are on the left. They are classified based on their shape. So an E0 would be nice and round, and then the higher the number would indicate the amount of flattening of the galaxy. Imagine you had a tire, and the tire was losing air. It was flattening, getting flatter and flatter. Well, a car tire might not ever be able to get that flat. How about a beach ball? You puncture a beach ball and let the air come out of it and it flattens down. So an E7, think of it as a very, very deflated, flattened out galaxy. Then they see these galaxies that we call S0. S0 are galaxies that have just a little tiny bit of an indication of the very, very beginnings of spiral arms, just sort of like the buds. But the arms don't go anywhere. They don't seem to wrap around the galaxy very much. That's just the sort of in-between galaxy classification between elliptical galaxies and what we call spiral galaxies. Now, spiral galaxies have the spirals. And if they have a round nucleus, well, they're just called regular spirals. They're just called spiral galaxies. And if they have a barred nucleus, if the nucleus is shaped like a candy bar, then they are called barred spirals, or SB for spiral barred. The next thing he did to classify galaxies, Edwin Hubble, was he classified them by how tightly the spirals were wrapped around the galaxy. If the spirals were wrapped around the galaxy, if they went around more than one complete time around the nucleus, like 1.5 times around the nucleus, then he gave them the letter A. That is a very tightly wrapped galaxy. If the galaxies went around if the spirals went around about once around the galaxy, well, then he gave it the lowercase letter b, because they're not quite as tightly wrapped around the nucleus. If the arms don't even go around once, if they went around about half a time around the galaxy, about 50% of the way around the galaxy, well, then they got the letter C. So to classify a galaxy, what you need to know is, first of all, does it not have spirals? Then it's elliptical. And then what's its shape? Is it E0, E1, E2, E3, E4, E5, E6, or E7? If it has just the very beginnings of spiral arms, it's S0. Or if it has spiral arms, well, then it's either a spiral galaxy or a barred spiral. Are the arms tightly wrapped? Then it's an A. If they're intermediate, it's a B. Or if they're loosely wrapped, it's a C. So this gives us all the classifications of galaxies that Edwin Hubble came up with. But there are galaxies that don't fall into any of these, and those are called irregular IRR. Irregular galaxies are ones that defy this classification system. Here we see a slightly different version of this classification. I don't think this one is quite as clear, as good as the other one, but the good thing is this one does include irregular. Notice the IRR. That's a galaxy that you can't really put in any of the categories. So I'm including that here. Also, this one leaves out the S0. So when Edwin Hubble looked at many, many galaxies in the sky and measured their wavelengths of the light they were emitting, what he found was that almost all of them were redshifted. And the ones that were nearby, that appeared bigger, were less redshifted, meaning they weren't moving away from us as fast. And the ones that were farther away, that were really small most of the time, they were moving away super fast. So this is what led him to the conclusion that the universe was expanding. Well, redshifts are just a type of a Doppler shift. So in order to understand about the development of the universe, the expansion of the universe, you kind of have to know something about Doppler shifts. The Doppler shift is the apparent change in frequency and wavelength of a wave from a source that is moving relative to the observer of the waves. So, if a source is moving toward you and sending out waves, what kind of waves? Well, they could be sound waves, or they could be light waves, any kind of waves. If they're moving toward you and sending out waves, that changes the wavelength. If they're moving away from you and sending out waves, either sound or light, that changes the wavelength also. Or if you are moving toward the source of the waves or away from it, that also changes the wavelength. That's why it says relative to the observer. So either if it's moving or you're moving, or if both are moving, it changes the wavelength. You might be familiar with this if you've ever heard a loud noise. What's loud? Well, a fire truck is loud when its siren is on, or an ambulance when its siren is on. Something that makes a loud enough noise that you can hear it from far away. Well, if a fire truck is just parked there, not moving, turns out doesn't matter which direction you're in. If you're in front of it or behind it, you hear the same sound, the same wavelength. But if you're in front of a fire truck that is moving toward you, well, you don't hear the same sound. What you hear is a higher pitch sound. Higher pitches have a higher frequency, which means a shorter wavelength. The wavelength is actually compressed because every sound wave the fire truck sends out is sent from a different location, which is actually closer to you, which compresses. So in these three images, the top left, the middle, and the bottom right, we see waves being emitted from a source. In this case, let's call them sound waves. They're being sent out in all directions. So notice the one on the top left, because the sound waves are traveling out in all directions and the object is not moving, they're all evenly spaced. That does not have any Doppler shift. But for the object in the middle, well, it is moving to the right. So you can sort of see how each time it sends out the next wave, it's coming from a different position, which is closer to the wave on the right that it sent out previously and farther from the wave on the left that it sent out previously, which winds up compressing the wave fronts in the direction toward the right. So if you were on the right of that object, you would hear a higher pitch. And if you were on the left side of that object, you would hear a lower pitch because you'd be behind it. It'd be moving away from you. The bottom right is a special example when the object is moving at the same speed as the wave. This can happen with sound because it is possible to travel at the speed of sound. We call that Mach 1. Mach 1, the speed of sound, about 760 miles per hour. If you move at that speed, then all the sound waves you're producing are traveling at the same speed you are. So you're keeping up with them in one direction. Then you make more sound, and it also remains with you, travels at the same speed you're traveling, and that eventually builds up to make a giant boom, what we call a sonic boom. So the object on the top left is a non-moving object. The object on the bottom right is moving at the speed of sound, producing the sonic boom. The same thing happens with light waves. But light waves, we don't hear, we see them, and the way that we see them is by their color. It turns out that every different color of light has a different wavelength. It just turns out that red waves are longer and blue waves are shorter. Violet waves are the shortest of the colors that we see, and everything in between in the color spectrum. So if the same thing happens with an object moving rapidly, sending out light waves, well then an object that is moving toward you is what we call blue shifted. It's shifted toward the violet end of the spectrum. For simplicity, they call it the blue end of the spectrum. And if something is moving away from you, well, it's shifted toward the red end of the spectrum. The wavelengths are made longer. They call that a redshift. So redshifts occur because the light waves are stretched out, because the object is moving away from you. The galaxies are moving apart from each other. So when Edwin Hubble noticed that pretty much every galaxy, almost every galaxy in the universe, was moving away from us, he realized the universe must be expanding. How was he sure they were moving away from us? By their redshift. And the galaxies that appeared to be close to us, usually they were bigger, they just happened to be closer to us, they weren't moving that fast, just a little bit. The galaxies that were far away from us were moving really fast. So the farther away the galaxy is, the faster it moves away, like in the raisin bread dough analogy. Even in the balloon analogy, that works. So whatever the wave started as, if it gets blue shifted, it becomes shorter. If it becomes red shifted, it becomes longer. Now, I'm not saying that colors are always turned to blue or red. They're just pushed in that direction. The only problem with this is that if you want to know how much a color has been shifted to the red, if it's moving away from you, you really have to know exactly what color it was to begin with. But we do. If you remember the spectral lines lab that you probably had in chemistry, I would love to do it again with you. And it's one of those things that it's really hard to do on a video. This is one of those labs I would consider doing if we came back and were in person at school. It's just a great lab, but you kind of have to do it in person. Well, if you remember the spectral lines lab, if you've done that one, then you know that every element has a very exact signature wavelength. Not just one, it has several signature wavelengths. So we know what those wavelengths are. And if we find one of those and we see how much it's been shifted, well, then we know exactly how much it's changed. Now remember, just because we call it a redshift does not mean that the colors are actually turned red. Notice that the second one down, the yellow wavelength, well, it still kind of remains yellow, maybe a little more orange now, but it's shifted toward the red end of the spectrum. That's what we mean. So the amount that the spectral lines are shifted toward the red is proportionate to the galaxy's distance away. So the farther a galaxy is away from us, the faster it's moving away from us, and the redder its light is shifted. If you remember the raisin bread dough analogy, or even the balloon analogy, then it kind of makes sense that this would work. So looking at all this information, Edwin Hubble was looking at these galaxies and measuring how much they'd been redshifted. He figured out the farther, the redder. He came up with the idea that the universe was expanding. Every bit of evidence since then has confirmed that. Now, I'm not trying to say that every galaxy is moving away from us, because that's not true. There are just a very, very few nearby galaxies that are not moving away from us. But if you get beyond a certain distance, every other galaxy, every distant galaxy is definitely moving away from us. And the farther they are, the faster they're moving away and the redder they are shifted. So if you saw a galaxy and its wavelengths were blue shifted, what would that mean? That would mean the opposite, that instead of moving away from you, it's moving toward you. Or you could say you're moving toward it, because it's all relative in space. No one is really standing still in space. There is a galaxy that is doing this. It turns out the Andromeda Galaxy is extremely blue shifted. In fact, the Andromeda Galaxy is going to collide with the Milky Way Galaxy in about 4 billion years. That might sound like a long time, but actually that is before the end of the solar system. That is before the end of our sun's lifespan, when the Earth will probably still be around. So by the end of the Earth's existence, it probably will be in a combined galaxy of the Milky Way and the Andromeda Galaxy that will have collided and merged into what they're calling Milkdromeda. Not a great name, I know, but that's seriously what they are calling it. So on the galaxy identification assignment, you are going to be classifying these galaxies, these images, into Edwin Hubble's categories. Now, part of the reason we're doing this is just to give you a sense of that there are so many galaxies and different types of galaxies. Also, so you can classify the Milky Way Galaxy that we live in. I did not actually give you the specific designation, the specific classification of our own galaxy. So that is the end of the notes on galaxies.